Welcome everyone. Thank you for joining us for the latest installment of our new Gleeble webinar series. Today's discussion will focus on dilatometry applications. My name is Daniel Quigley. I'm the Director of Business Development and Marketing here at DSI. As the invitation to this webinar mentioned, dilatometry is one of the most popular applications studied in the Gleeble. In some cases, tests can be fairly simple. Other times they can be complex and last for hours or days. But regardless, it's important to review best practices and test setup to ensure accurate, repeatable results. Today, Dr. Brian Allen will provide an overview of the application and discuss the value of dilatometry, followed by Mr. Eric Deitz, who's a System Service Engineer here at DSI, who will provide more detail on best practices and procedures for performing dilatometry tests. For those of you who have joined us for previous webinars, welcome back. You likely know how this works. To our new attendees, I'll give a brief summary. Our goal will be to keep this webinar to 1 hour or less. If time allows, we will have Q&A at the end of the presentation. If you have questions, please submit them using the chat feature here in the webinar. We have a couple of our Gleeble All-Stars here on the line with us. We have Brian Smahosky and Sean Garrity. They're here to answer questions directly in the chat or during the presentation, or we may be able to address some of the questions during the Q&A portion of the meeting, again, as time allows. As I mentioned last week, we have been pleasantly surprised by the response to the webinar series. We have over 350 people signed up to attend today, and as we look through the organizations that are represented, it's an impressive list. So if you're listening to this, you're in good company. But unfortunately, with this many people, we probably won't have enough time to address every question. However, we will do our best, and we will follow up after the webinar as needed. A couple of hours after the webinar, you'll get an email with a link to download the presentation. It'll be a single PDF file, as well as a link to view a video of the presentation. And I think we've also submitted, we can provide that link here in the chat as well. It may take a little bit of time for this latest video to become active, however. Please also mark your calendars for next week's webinar. It will take place at the same time on Thursday. An invitation will be coming to your inbox soon. It's my pleasure to introduce our presenters. Dr. Brian Allen is our chief metallurgist. He's been with DSI for about 10 years and has traveled to all parts of the world to work with Gleeble users to help them get the most out of their system. Following Brian, Mr. Eric Deitz will present. Eric has also traveled the world for us to install, calibrate, and maintain systems, as well as train our Gleeble users. So we're in good hands. Brian, I want to thank you for preparing your presentation, and I'll hand this over to you. The floor is yours.
Okay, thank you very much, Dan. I'd just like to repeat Dan's welcome and thank everyone for their attendance. We understand that you're all very busy and you all have a lot of things to do, so we do appreciate the time that you've chosen to devote to spending to us and learning about Gleeble dilatometry applications. So without further ado, I'll get started. As Dan said, my name is Brian Allen. I'm the chief metallurgist here at DSI, and I am just going to go through some background of dilatometry, what dilatometry is, what the typical uses of a Gleeble for dilatometry are, and then following my introduction and brief presentation, Eric Deitz will talk about best practices for actual setup and programming of dilatometry applications in the Gleeble. So what is dilatometry? This slide simply shows the definition of dilatometry. So a dilatometer, according to the dictionary, is simply any scientific instrument that measures volume changes caused by a physical or a chemical process. These typically are thermal expansion, phase changes, dissolution and or precipitation reactions, and densification, such as may occur when you are sintering a powder compact or in our world, a powder metallurgy part. So we often don't think about it, but the picture here shows a standard just alcohol thermometer. A thermometer is actually a dilatometer. So how does the thermometer work? A thermometer has a volume of alcohol or mercury here in the tip, and the thermometer actually measures the expansion of this liquid as it gets pushed up into a capillary tube as the temperature increases or decreases. So in reality, a thermometer is simply a dilatometer, and it is measuring the expansion of the mercury or the alcohol. Now we calibrate the thermometer to a temperature, so we actually use that dilation of the mercury or the alcohol to measure temperature. That's a little bit the opposite of what we do in a Gleeble. In a Gleeble, we typically know the temperature by other means, and then we're actually measuring the expansion of the material. But in essence, it's exactly the same thing that we're doing. And of course, over the right here, we can see a very simple, elementary school science fair experiment that shows that heated air expands as we put a bottle full of air in either bath of ice water or heat it up on a burner. We can see the air inside the balloon expanding. So essentially, that's all we're doing in a Gleeble is we're measuring the expansion of a metallic sample, in our case, as we heat and cool the material. And of course, as we heat them and cool the material, there's a lot of things that happen in a metal that are a lot more complex than what I've just described. Obviously, the coefficient of expansion is, essentially similar to what we've talked about already. Coefficient of expansion is fairly simple. It's fairly easy to measure. It's usually for metallic materials reasonably large, so the resolution of the measurement that you need to get a good coefficient of expansion is not really that difficult to achieve. The other thing, and probably the primary thing that people use Gleeble for in dilatometry mode, is to measure phase changes. Phase changes are critically important in the treatment of steel, as the steel changes crystal structure from ferrite to austenite and can absorb a lot more alloying elements in austenite, and then typically we quench back down at a fast cooling rate from that austenite in order to get several of the different structures that you can get in steel, perlite, martensite being two of the most common ones, also of course bainite, and then the spheroidized carbide, perhaps if we cool very slowly and let this perlite carbides spheroidize. Alpha and beta titanium are also very critical. There are a lot of titanium alloys that are designed around the alpha beta titanium transition. Alpha beta titanium transition is a much lower volume change transition than the ferrite austenite transition in steel, so it's a little more difficult to measure, but still can be measured in dilatometry. The third primary thing that people use dilatometry in metallurgical research for is for dissolution and precipitation reactions. Now, these are actually often quite difficult to measure. The precipitate in a metallic material is usually a very low volume fraction of the entire material. Therefore, even if you have a reasonable density change from a solid solution material to a precipitated material within a metallic sample, if you only have 2, 3, 4% volume fraction of that precipitate, it can be very difficult to measure that using dilatometry. And often the products of precipitation have a relatively small density change from the solid solution. So combining these two together means that it can be quite difficult sometimes to measure dissolution and precipitation reactions, but not always impossible. So just something to keep in mind. I'll segue here a moment into talking about a couple of the ways that we measure the dilation of a sample in the Gleeble. This shows our non-contact optical dilatometer. So this is a green LED light-based device that measures the diameter change of a metallic sample as we heat and cool it in the Gleeble. Now, I would like to point out that we do dilatometry a little different than most other manufacturers in that we usually measure the diametral change of a round sample. A lot of other machines are configured to measure the length change of a sample, and there are reasons that we do this, and I'll get into those in a little bit, but just keep in mind throughout this presentation that we do measure the diametral change typically when we're doing dilatometry in a Gleeble, and that is a little bit different from most of the other equipment that is out there. I won't go into a lot of information on the optical dilatometer. It's a very nice device. It doesn't require a lot of setup. Once you have it attached to the Gleeble vacuum tank, you don't have to clip on off the extensometer, so it's got some benefits. It does have some high temperature limitations, although the newest model is quite good. It has enough high intensity light to measure the dilation of a sample even at quite high temperatures when the sample may be fluorescing quite strongly as well. Probably the more common device that people use in the Gleeble to measure dilatometry is the clip-on LVDT mechanical contact dilatometric transducer. So this is simply a mechanical device. It has a linear variable displacement transducer, or a length change measurement sensor. It has two quartz rods that simply clamp onto the round sample. So the sample goes here in the contact area between the end of the straight rod and the curve of the L rod. And then there's a slight spring tension that keeps the sample clamped firmly between the rods, but hopefully not too firmly, and we'll talk about that a little bit later. But this is a very simple, easy to use device. It's a little bit cheaper than the optical dilatometer, so it's also very widely used in the Gleeble for measuring dilometric expansions. So I'd like to take just a moment to talk about the benefits of the Gleeble when you're doing dilatometry. So the Gleeble is a bit unique in the world of scientific simulation equipment in that we use direct resistance heating to heat our sample. So what this means, and I'll compare and contrast this a little bit to induction heating, although the same points will apply to furnace heating. So in a Gleeble, we clamp a metallic sample between two, usually copper, maybe stainless steel, but between two grips that are mounted in water-cooled jaws. So what we get with the Gleeble, since we're using direct resistance heating, we're using a current to heat it, and that current has a equal current density on the surface of the sample as well as in the center of a sample. That means that no matter how large my sample is, 10 millimeters diameter, 15 millimeters diameter, I am heating the point of material at the center of that sample at the same rate that I'm heating a point of material on the surface of the sample. Since that current density is constant, I'm able to heat the center, the mid diameter, and the surface of the sample at the same rate. So the important part of that is that I get an isothermal plane across this diametral plane of the sample. So I don't have a hot spot on the surface while I have to wait for the center to heat up and get hot. Now, if we compare that to induction heating, as we know, does have a skin depth, so it does heat a little bit into the surface of the sample, but the skin depth, depending on frequency, is usually quite small. So in essence, induction heating is very similar to a furnace heating in that we are really only heating the outside of the sample, and we have to let that heat soak into the center of the sample. Now, if I'm trying to do a dilometric experiment at 1 degree C per second, 5 degrees C per second, maybe even 10 degrees C per second, it's not really critical because I have plenty of time for that heat to soak into the sample, and the thermal gradient I'm developing is probably very small. But if I'm trying to do a welding experiment or something that has a very high heating rate, like laser cutting or torch cutting, I am not going to be able to heat at those kind of rates in an induction heating or in a furnace system and keep a good thermal gradient through the sample. So what that means is the surface is going to heat first, the center is going to be cold, and I'm going to get a little bit of a distortion in my dilatometric curves. The curves are going to broaden and they're going to shift because I'm not really measuring the surface temperature through the whole sample. I'm just looking at the surface temperature. The center is colder, so I'm not going to get a real good result from that. The same actually holds true on cooling. So again, in resistance heating, looking at the picture on the left here, we have a Gleeble sample that is primarily cooled by these copper grips, and these copper grips are in these water-cooled jaws. So what you get in the Gleeble setup is almost all the heat, not all of it, but almost all the heat in the Gleeble sample is actually being extracted through the ends of the sample to the water-cooled grips. That means that I keep a fairly, even on cooling, this isothermal plane, remember we're measuring in the diametral direction here, this isothermal plane maintains approximately the same temperature at the surface as it does in the center, because the primary heat loss is not to the surface and in radiation out to the environment, but through these water-cooled jaws, again, keeping an isothermal plane in the center. This means that I can cool at a very, very fast rate. I can maintain that isothermal plane in the center. Compare that to an induction heater where I'm probably quenching on the outside because I'm not extracting much heat through the quartz push rods here. My surface is going to cool faster. If I quench on the outside, I'm going to cool the surface much faster. The center is still going to be hot. And again, I'm going to get thermal gradients in my measurement that are going to affect the results of my measurement. With the Gleeble, we even have one more trick that we can get even faster cooling rates while maintaining that isothermal plane in the center as we cool the sample. This is a picture of what we call our IsoQ Quench setup. That stands for isothermal quench technology. If you look at the lower right of this sample, you see a cross section of an IsoQ sample, and it has two hollow ends. The measurement center is solid, but each end is hollow, and we're able to inject coolant, either air or water, into this hollow end, and this is on both sides, although only one side of the sample is shown cut away. We can inject quenching fluid into both sides of the sample. So again, similar to when we have this clamped in cooled water in copper water-cooled jaws, we get a very, very fast heat extraction rate from the ends of the sample. But again, the heat flow is almost entirely axially through the sample, which means we can get very, very fast cooling rates, while again, measuring dilation in the diametral direction in the center of the sample, where we keep an isothermal plane, surface to center to surface, so we can get very sharp dilation curves, and we can get very good temperature readings of where these transformations occur. So I'm just going to move on a little bit to the actual data that we get out of the dilation plots here. This is just this example of a pure nickel sample that's heated from room temperature to about, I think, 1050, 1100 C here. And this is a simple thermal expansion curve for nickel. It shows no phase changes. And so this is about the simplest dilation plot that you can get. And you can see that the heating and cooling curves fall directly on top of each other. So this is what you typically want. And so as this is a single phase material, we don't have a lot of complications here. We can see that the thermal expansion does change a little bit as the sample heats up. So it's not absolutely linear, it's slightly curvilinear, which is what we would expect based on the physics. But again, just a very simple example of the data plot that we typically get from a dilatometry setup. Of course, if we go to a material that has phase transformations, we get a little more complex plot. This is a simple dilatometric curve. Actually, this is three curves laid on top of each other. So three different experiments with three different samples. So very good repeatability here. This is a low carbon steel heated or cooled, excuse me, at 10 C per second. And I don't know what the heating rate is, probably about 10 C per second as well. But here we see several different phases. So as we initially heat, the on-heating curve, this is simply the expansion of the ferrite. Then we hit a temperature where the ferrite starts to transform to austenite. We get the transformation, and then once we've 100% transformed into austenite, we start again on a linear expansion of the austenite. Then at some point we hold for a few seconds before we start to cool, and then we start to cool down, and we see the thermal contraction of the austenite. Again, we see that phase transformation going back the other way as we cool, austenite to ferrite, and then we see the linear contraction of the ferrite as we continue to cool down. So one thing to notice on all these curves is that there is an energy barrier to be overcome for transformations. So once we get to that point where ferrite and austenite are equally energetically favorable, we have to provide a little extra energy, either heating or either overheating or undercooling, depending on which direction we're going, to make that transformation happen. So what this means is that transformations are delayed a little bit until there's a sufficient thermal driving force to drive that crystallographic transformation. And there also can be some nucleation times involved. So if I was doing a quasi-static experiment where I was heating very, very, very slow and cooling very, very, very slow, I would still not have much of a nucleation time because I'd be going slow, but I would have a energy barrier to overcome. I'd still need some superheat or some undercooling to get these transformations to proceed. So, and you see that in the austenite to ferrite transformations are off shifted, whether I'm doing an on heating curve or an on cooling curve. One of the other things that's important to mention, and one of the big benefits that Gleeble has when doing dilatometry, is that speed matters. I've spent some time explaining why we can get good measurements at very fast heating and cooling rates in a Gleeble, where that may be more difficult to get in some other machines. So the faster the cooling and heating rates are, the more these temperatures will shift based on the heating and cooling rate, and therefore the more that Gleeble technology becomes an important factor in being able to gather accurate data here. So this shows, again, the same low carbon steel. This is a cooling curve at 10 degrees C per second and the cooling curve at 200 degrees C per second. So I believe these are probably heated at the same rate. So you see there's not a lot of difference in the heating curve here, but you can see a significant shift of the transformation temperatures on cooling to a lower temperature. And again, that's based on that nucleation rate that I talked about, and the fact that that you need a little more undercooling the faster you're going to kick off that reaction faster. So speed does matter, and that's why some of the Gleeble features are very important when you're doing fast dilatometry for fast heating and cooling for things like, say, welding or other applications where you have rapid heating and cooling rates. So I've mentioned a little bit of possible transformations that could occur in steel, and primarily steel I'll be talking about, although there are transformations in many other materials. So steel is a very, very useful engineering material because it does have very many multiple stable and metastable phases. So depending on the properties that are needed in the final product, we can have steels that are austenite, ferrite, pearlite, bainite, martensite, or mixtures of any of these different phases. And which of those phases depends on, of course, the alloy and chemistry distribution of the alloy in that part, but largely depending on cooling rate, holding time, and the final temperature that we quench to. So it becomes a very big challenge, I guess, in the steel industry to develop these process maps which show which of these phases will develop under different holding times, different cooling rates, different processing parameters. So if we plot all those onto one curve, we get what we call a continuous cooling transformation curve. So this is simply a curve that shows some maps of different structures that can be formed on cooling of a steel and cooling rates, faster, moderate, and slow cool. And if you superimpose those cooling rates over this, I'll call it a structure map, you can predict based on the experiments that have been done in using dilatometry, what phases you're going to get. So one of the tasks of many metallurgists that develop a new alloy is to develop these continuous cooling curves for their new material, their new alloy, so their customers know how to process this material and get the microstructure that they're looking for, be that benitic, ferritic, pearlitic, martensite, or dual phase. So this is simply a schematic curve. Another way to plot it here is a little more realistic curve, not quite so schematic. Again, shows different cooling rates, slower cooling rates, faster cooling rates, or you can also have isothermal holds. So I can cool down to 600 and hold for a certain amount of time, or at 400 and hold for a certain amount of time, like is illustrated with these green arrows. And I can predict then, based on the previous work that was done in the dilatometer, I can predict what phases I'm going to get in that steel alloy. I will mention that usually these curves are on a linear scale on the temperature axis, but a logarithmic scale on the time axis. So a linear cooling rate, ends up projected as a falling cooling rate here, and of course a isothermal hold is just a flat horizontal line. This just illustrates a little bit what I have just described a little bit, is that the alloy is very important here. So this is simply the two CCT diagrams for the same steel, except one has no manganese. It's a 0.4% carbon steel. One has 2% manganese. So you can see the manganese shifts all these curves over to the longer timelines. So we would say this steel has a better hardenability because I can quench in martensite much easier in this steel. So it's a more hardenable steel. And manganese is, of course, well-known hardenability element. Chromium, molybdenum, boron, or other hardenability elements that can delay some of these transformations and allow this steel to be more easily hardened, hardened with a lower quench rate. And of course, if I have a lower quench rate, I can avoid some quench crackings and some other problems. This slide discusses how to create a CCT diagram with the Gleeble. So the Gleeble does come with an option to not only do the dilatometric work to determine where these transformation points are, but to also plot them on a CCT diagram. And I won't talk a lot about this piece of software that comes with the Gleeble, but I just wanted to point out that the Gleeble does have a software package that is available that can take the data you generate from the Gleeble Dilatometry at different cooling rates, plot it on a map, and create a CCT diagram for any given steel that you may be working with. I'm just going to go over in these last couple slides before I wrap up my part of this presentation a couple of questions that we often get about dilatometry curves. So theoretically, a dilatometric loop, as I'm going to call it, a heat up, transformation, cool down, retransformation, and then cool back to room temperature. Theoretically, that loop will close if everything is absolutely perfect, but in practice, this rarely happens. So we see in this diagram, I have a couple things going on. One, I don't totally close the loop, so I've got a little bit of permanent change of diameter here, illustrated by these two opposing arrows in the lower left of the graph. And I also have a little bit of a decrease in diameter here at the hold time when I transition from heating to cooling. So I'll talk a little bit about what can cause these kinds of issues. So the primary thing that we get, and why dilatometric loops don't always close, is the phase that you end up with after doing a dilatometric experiment is often not the same phase that you start with when you started your dilatometric experiment. So this graph actually shows three different curves, and they're very repeatable. So you can see that it's not a problem with the repeatability of the system. But what I suspect is happening here is that I probably started with a sample that had a little bit of bainite or martensite in it. Then at 10 C per second, after I heated that, austenitized it, recooled it, I probably ended up with a sample that had a ferritic plus carbide microstructure. So we all know that the martensite expansion has more volume than a ferrite plus carbide phase. So I suspect in this case that's what's happening here. I don't know that for a fact. Another thing that could be happening is these are rolled samples. So whenever you do a rolling deformation, you actually get a texture in the material. So the material will not be truly isentropic, but I will have a rolled texture that will have preferential crystallographic orientation through the product. And once I heat that product up and cool it back down, I've now randomized that texture, and I've probably changed the dimensions a little bit simply because different crystallographic planes have different densities. And if I change those crystallographic planes, I will change those densities. Now that's a very small effect. I doubt that's what we're seeing here in this graph, but it is something else to keep in mind. The other thing is that there is never truly zero force in a dilatometric experiment. We discussed a little bit how we clamp the sample into some copper water-cooled jaws to get great cooling rates and maintain isothermal planes. But obviously, when I clamp that sample into the jaws, I am putting a little bit of force on that sample. We allow the sample to expand and contract in the Gleeble using some very low friction bearings, but we're still having to conduct electricity to that sample. So there's a little bit of a spring tension in the cabling that we try to reduce as much as possible in Gleeble testing, but there's never really truly zero force on a dilatometric sample, because even if I could achieve a truly frictionless environment, the sample itself has weight. So I have some force on the sample, and that stress can cause a little bit of directionality in some of the transformations, and also a little bit of a creep. In fact, the arrow here at the upper right of the attached graph, I suspect is a little bit of creep that has happened at holding at high temperature, where the quartz rods, where they have a single point contact with the sample, have either indented the sample a little bit, or the quartz itself has just indented a very minute fraction and creeped a little bit in the sample. Now I will mention that even I've seen examples that are much worse than this, and the temperatures of these transformations are still quite good. So a little bit of creep doesn't really affect those transformation temperatures very much. So it may not be something to worry about, but if you're looking for a really pretty graph to put into a publication, it might be something to be aware of. The other thing is that the dilatometer rods themselves will heat and expand a little bit. The dilatometer itself is cooled, so we get very few temperature effects there, but the quartz that we choose for those dilatometer rods are obviously very low thermal expansion. That's one of the reasons that quartz is used for these applications, but that does have a little bit of thermal expansion. And so a little bit of expansion of those rods can give you a little bit of this failure to close on some of these loops. But again, not usually a problem. And if you look at even peer-reviewed publications in the highest rated journals, you will see some dilatometric curves that quite frankly don't look all that great and look much worse than this one I'm showing here. So possibly nothing to spend too much extra time worried about, but it is useful to think about it. So as my final example of dilatometry, I'll thank you with a picture of this nice hot air balloon, because again, a hot air balloon works by the dilation of air as it's heated. And we've been talking about how things expand and contract as they're heated, and that is how a hot air balloon works. So that concludes my portion of the presentation. At this point, I'd like to hand the presentation over to System Service Engineer, Mr. Eric Deitz, and he's going to be talking about some of the more practical details of how you set up these kind of experiments in a Gleeble. So Eric, it's all yours. All right, I'm not hearing anything, Eric.
Yes, I'm there, Brian, thank you.
Okay.
I'm just trying to show my screen. Thank you. Thank you. All right, good morning or evening, I suppose, to most of you, perhaps. As Brian said, those of you who don't know, I'm a service engineer here. My name is Eric Deitz. I'll be talking a little more on the operational side of this now that Brian's covered a lot of the theory behind it. So just a quick mention of the agenda for what I'll be talking about. I'll mention the different devices that we have in service with the Gleeble, the C-gauge dilatometer, and the multiple micrometers that we have. I'll talk a little bit about the CCT work in the standard jaws, as well as in the low force jaws. A brief mention of the IsoQ setup. Brian's already given most of the important points on that. I'll mention a little bit of the mounting setup, since I'm not sure everyone's familiar with the fact that there are multiple options for the contact gauges. Cooling the contact gauges is important, so we'll talk about that, as well as adjusting the heating cables in the low force jaws. CCT with compression, since that's an interesting topic that customers are interested in a lot of the time. And then just a few common CCT issues. We'll look at a few graphs and kind of try and quickly diagnose what may be going on. All right, so for contact gauges that actually sit on the specimen, as Brian mentioned, there's the dilatometer. There's also the C gauge, which probably predates the dilatometer. Certainly is useful in the same application. Both of those gauges are useful as a contact device will be, versus something like the micrometers, which are non-contact, in that there's no chance of a visual interference. So there's no transmitter, no receiver, so no worry about where the thermocouple is, if it's in the line of sight blocking the view, anything like that. You can place it on there as long as it's placed properly where you want it to be. It will not have other concerns in that regard, at least. The disadvantages, though, particularly for deformation, the gauge sitting right there on the sample can therefore be damaged. So for that reason, we always recommend to use a stroke compression limit in your QuickSim program to prevent that. If you're using a table program, go into the setup tab, I believe it is, and just set some limit that's less than that's going to prevent it from moving so far that it will damage your gauge, essentially. The other disadvantage, as Brian mentioned, which can be a little bit of a nuisance if you're running a lot of tests, is that you have to remove the gauge and then remount it every time for every new sample, which increases the setup time some. Once you have everything else set up, it doesn't take a whole lot of time, but it's not as convenient as not having to replace it. And it can increase the variability if you're, if you run 100 tests and so you're not watching it so closely. There's a little bit of variability potentially in that. Between the two gauges themselves, there's some differences. The C gauge has a significantly larger range, almost 3 times as much, but the resolution's significantly reduced, so about a factor of 5 or so. So the dilatometer has significantly better resolution if you have, very subtle transformations that are very subtle volumetrically. The CCT dilatometer will be definitely a better bet. If you expect to have much more significant change, though, you may have to use the C gauge instead. Now, the other side of the coin is that we have non-contact micrometers. 2 models that we currently provide, although one's largely a legacy option. Those are models 39112 and 59063. The 59063 is shown in a computer-generated image in the bottom right there. So kind of conversely to what the contact gauges have advantageously, the micrometer is perfectly safe from damage unless your sample really explodes or something and goes right through the glass on the other side through which the micrometer is watching. But generally speaking, micrometer is safe from damage from your dilatometry tests, and so you can not have to worry about that at all. And just once you have adjusted, there's no need to readjust the dilatometer. If your test doesn't change, it's a different sample, but same dimensions, same presumed location of interest for the dilatometry itself, you can leave your micrometer just as it was, and it should work, very, very similar the next time. Another advantage that Brian mentioned a little bit is that those, since they're simply LEDs, can be oriented any which way we want, really. You can use them for both crosswise and lengthwise measurements. Again, we don't do a whole lot of that for dilatometry with the Gleeble, lengthwise, I mean. But for other applications, just more general deformation, the option is there. So that is a nice advantage that they have. The disadvantages of those devices, though, are that, as I mentioned before, visual interference is a concern. If I've seen it where in uniaxial compression testing, for example, trying to run that in an inert environment with the micrometer, the nickel paste eventually starts to outgas and everything inside the chamber, and then that is enough to really interfere with your reading. Or if the thermocouple, as it heats, it relaxes a little bit, and so it kind of shifts position and comes into view, comes into the line of sight, that can affect your reading. So that is something to keep in mind when using the micrometers. Also, for newer users who haven't done it a handful of times, the initial alignment to get the beam to go properly from the transmitting head to the receiving head is a little bit challenging. It takes a little bit of getting used to. I think most of the guys in my department can tell you, a few minutes and they'll have them set up nowadays, but that takes a little bit of practice. So newer users find it to be a little bit challenging. A little more specific information about the 2 micrometer models. The 39112 model, as I mentioned before, it's largely a legacy model at this point. Series 3 systems and the older GTC systems are what can use this device. Specifically in terms of the GTC system, that kind of differentiates at the in terms of which wiring you have. So there may be a label on your load unit which mentions wiring revision, may say Rev J, Rev K, something like that. The pre-Rev K machines are electrically compatible. The wiring is compatible with the 39112 model. The subsequent wiring revision, so Rev K, as of this point in time, is compatible with 59063, which is, I believe it's a newer model. It's higher power, the range is more significant, the sampling rate is more significant. So it has more benefits largely, greater applicability. The higher power allows it, for instance, to better, the beam to be kind of bent in different ways more so that you can use it with the tracking mirror setup that we have to try and follow the dilation during deformations, things like that. It's a little more applicability. So CCT in the standard jaws, either the standard jaws in the pocket jaw or the hydro wedge will presumably be the means in which you'll do deformation dilatometry. The low force doesn't really lend itself to that so well unless it's significantly lower force, and that's a little bit of an extra complication, I suppose. The standard jaws, though, can be used just for purely thermal dilatometry with no deformation intended. They can be used for that. The low force, not every customer has low force, so it's an available, it's an option if that's not available to them. All you have to do in that case is just make sure your mechanical system is on and try to maintain zero force as best you can with the sample. So I show in this program example right down here, you simply would turn on your mechanical system as such, and then give it some time, a little bit of time at the beginning of the program, as you normally would with most other thermomechanical tests of this nature, to reach a zero force condition and then try and hold zero force during the test. It does a pretty decent job. It's still low force does a better job, I would argue, certainly, but it does a better job than you might think having not tried it. But the low force jaws are really what's kind of meant for dilatometry work. Do a very good job with that. The jaws themselves, as most of you probably know, have a ball bearing system that slide along those black shafts back here, and so they slide through with minimal friction. And if set up correctly, there should be negligible load in your sample with these. So it's a pretty good option for dilatometry. I'll briefly touch on IsoQ setup. Brian did a good job of already talking about most of this. As he said, enables internal quenching, which is difficult to do otherwise, really. You can do external quenching with dilatometry, but that leads to more complications. The benefits of the internal quenching are obviously that you can maintain vacuum. There's not a concern in that regard. And if using the micrometer, again, also, it's therefore not going to interfere with the micrometer reading at all. Blasting water around, maybe potentially moving your thermocouple, everything else might cause some problems otherwise. So internal quenching is very useful for that. And as I believe he mentioned, it can be used for gas liquid quench media. Both of them work just fine with that. So Brian already talked about the general geometry. Again, shown here, there's a hole bored through most of the way, not quite all the way into the sample. That's our typical geometry. That maintains a pretty good radial isothermal plane, and cooling rates up to 400 C per second are reasonable to expect in this. We can go higher than that. We have designs for samples that bore the hole all the way through the sample, which you can get significantly higher cooling rates, 1000 C beyond that. But from some of the testing that we've done in the past, the isothermality of the radial plane is not maintained at that point, since you're going all the way through the sample. So that's it. To get really the best data you can get, it requires a little more work in that regard. We have an app note that I can I think I mentioned later on in this that if you're interested, you can take a look at it and learn a little bit more about that. I'll briefly mention the mounting setups for these gauges, the contact gauges in particular, since I'm not sure everyone is familiar with the options they have. For the dilatometer, you really have two options. There's this mounting bracket I showed on here in this bottom picture, which is a nice option to have, as well as the rubber band option that most of you have probably seen and used. This mounting bracket is currently available for the dilatometer, not the C gauge. The C gauge doesn't really have a location on it which would lend itself to using this so well, but there's a nice flat bracket on the back of the dilatometer that rests very well on this slide bush right here. So the gauge rests on this ball bearing slide bush right here, which can move very freely along this precision shaft here, and you have quite a bit of freedom to move it with these different elbows here on the bracket. The benefits of this mounting bracket are that it's once it's been mounted, it's quite stable and consistent. It works very well in that regard, but it is a little more limited than the rubber band method. The rubber bands, on the other hand, can be used before with C gauge and dilatometer. Simple setup, just have these mounting rods right here and here, and rubber bands, 1, 2, how many you want, really kind of go between them, and then you stick your sample, or not your sample, your gauge right between there, right in the middle, and just kind of try and secure it the best you can. Now the benefit of that is you can kind of orient them however you want. You can do a lot of different things with that. But the gauge isn't as securely mounted, obviously. There's some more, if you're taking it out in and out a lot, there's more variability potentially in that. Less of a guarantee that you're going to be really nice and measuring just that, a isothermal plane. You're not going to skew it across the sample a little bit. That can happen with this more easily than with the mounting bracket method. One thing I want to touch on is the cooling to the contact gauges. I've seen it on an occasion or two, let's just say, where customers are using C gauge or dilatometer, but not using the cooling circuit that's provided. These contact gauges come with some hose and a regulator and an air hose that attaches to the load unit manifold in the back that can be used to cool the gauge while you're heating. So use air supplied from the Gleeble air water manifold in the back to keep it from overheating, potentially damaging the gauge. If you're having a long soak or just high temperature soak, your gauge may overheat, and that's really not desirable. There is a heat shield on the front of the dilatometer model, but it's still best that we can use the air passing through the gauge to try and keep it as cool as we can. So if at all possible, please do not ignore that cooling circuit. Your gauge will thank you for using that. Another important point is the heating cables in low force jaws. If they are not set properly, they can introduce some force. Brian mentioned, having excess force on your sample can show up in your data at the end in your actual plots of dilatometer versus temperature. And so trying to create a frictionless environment, a load-free scenario for your sample is the whole point of using low force jaws. So when I'm trying to get the best out of them, it's important to adjust those before you run your tests. So you want to load your sample in the jaws, use a wrench like I show in the left-hand side picture there to loosen the heating cables, the bolts that restrain them. Then you can just pretty easily kind of move them around and find a good position where they aren't still compressing or applying a tensile load to your sample. Retighten those bolts. At that point, you can remove the sample and wiggle the jaws and confirm whether it seems like it's not applying load at that free span right there that you have for your sample. So pretty simple. It only takes a few minutes, but worthwhile for your results. One One item that I'm not sure too many customers have seen before is this compression method shown here. We have these special IsoQ samples with threaded portions just before the shoulder that you can use these locking nuts shown here, and then a washer behind it, and then they'll rest against the grip and they can actually be compressed a certain extent. So you can compress IsoQ samples, which is, you gotta get the best of all worlds really in that regard. It is somewhat limited. You only have so much free span there before you compress so much that you're going to contact your gauge, if you have a gauge in there. But for that purpose, we have thinner quartz rods that are, the typical one is 5 millimeter diameter. We have 3 millimeter diameter quartz rods that are used, I think they're meant specifically for this application, that you can pretty easily configure to use for this to get a little bit more compression if you need an extra millimeter or so. This is detailed pretty well in application note 027, performing CCT compression tests. If you want more information on this, you feel free to let us know. We can provide you with that if you don't already have it. Since that is a pretty good option. The other CCT, the other compressive option with CCT obviously is uniaxial compression testing. That could be done in the general purpose MCU or the hydro wedge. You have the same capabilities for compression you have with either of them, but your cooling tends to be significantly reduced, so you don't have the option of the internal quenching. Micrometer is certainly better suited, I would personally say, to this application than contact gauges, since if any of you have seen hydro wedge before, you know how forceful the hydro wedge is during the formations, and I wouldn't personally want to risk breaking a gauge during that. So there's a setup for a kit that allows you to kind of interface the micrometer with the hydro wedge. I'd recommend using that in this scenario. It's a little bit of a challenge. You have to set up the micrometer beam pretty particularly so that you get the beam where you want it, where the sample will be after deformation. It takes a little bit of figuring out, but it's doable. I then just wanted to quickly show a few pictures of common issues that we see on CCT, and just really briefly touch on them. Brian already talked about one of them pretty well, but this one is one that we see a little bit every now and then. You kind of see that ideally you'd have a nice, constantly changing diameter dilatometry reading during this cooling portion, during the heating portion too. Really, it shouldn't flatten out too much, typically speaking. But we'll oftentimes see results like this, where it looks pretty flat here, and it's a lot flatter here than shown in this nice example over here, for instance, at least. I've seen it before where that is the case because, again, maybe you're using, whoever performed the test maybe was using the rubber band mount, and so the gauge was a little bit skewed. It wasn't really perpendicular to the sample. And so it's kind of measuring multiple planes, not really getting a proper isothermal planar reading. So you're kind of in that sense, kind of overlapping a lot of different planes, a lot of different transformations regimes in that sense. So it skews the look of your data. That's why I say be on the lookout for that. It's very simple to very easy to have your gauge, one of your contact gauges, skewed on the rubber band mounting method. This one Brian showed pretty well. I like this picture though, so I wanted to show it again anyways. This is a case, again, based on the compression right here. Or I suppose the sample's really kind of being exposed to a little bit of tensile force, essentially, I suppose, based on the fact that the dilatometer reading is dropping there, so it's being pulled a little bit. But that's a clear indication, again, of, as he said, that you have some kind of force in your sample. So you may want to look at reducing the spring tension on your gauge a little bit. As he mentioned, you may want to look at the heating cables if you're doing low force testing. You may want to consider altering the force control value you have, maybe make it just a little bit negative, a little bit positive, something. Since maybe there's a little bit of hysteresis in your load cell or something. Things like that usually cause this, as he mentioned. A third one, very obvious that you've pretty clear what's going on here. This is a micrometer micrometer graph, and then along with on the right again a pretty good looking one. But this one, as you can tell, clearly something's in the line of sight, something's interfering. Maybe that's the thermocouple again coming loose and getting in the line of sight. Maybe it's the wire, the thermocouple, maybe not the actual thermocouple down there at the bottom, but something's interfering with your reading, and you can get results look like this. I've seen this kind of thing before too. So at that point, you have to just go back in the tank and adjust a little bit, try to get rid of all that noise you have there. That's all the information I was going to provide. I wanted to just say thank you for listening, and I'll hand it back to Mr. Dan Quigley now.
Okay, thanks, Eric. Thanks, Brian, as well. Great job. As I mentioned, we did have a large group of attendees today. There's been a lot of great questions. I want to thank our panelists here, Brian Smosky, Sean Garrity. They've been furiously typing away and answering a lot of those questions. Unfortunately, we are about out of time, so I don't think we'll have time for a live Q&A. However, we have been documenting all the questions, and if any of the questions haven't been addressed directly in the chat, we will follow up. As I said in the past, we want to be respectful of everyone's time. We do want to end this within an hour. Unfortunately, that time is about up. Again, I want to thank you for spending the time with us. I hope it's been valuable to you. Thanks, Eric and Brian, for presenting, and our technical team. If you have technical questions about the operation of the Gleeble, please contact our service team. As I mentioned last time, they can't travel to you, but they are very good at providing remote support. They also have a new ticketing system and a method for making sure that requests get addressed very quickly. So the best way to contact Brian, Eric, Sean, and the rest of the service team is to email service@gleeble.com. That does create an automatic ticket, and we'll be sure to follow up with you as soon as possible. If you have any questions about how Gleeble research or Gleeble can support your research, please email me. Me and my team will get back to you. We can connect you with an application expert to help you find the right solution. My email address is in the invitation to this webinar. In closing, please be on the lookout for an email. In about 2 hours, you should get an email. It will have a link to download this presentation as a PDF, as well as eventually a link to this video so you can view this at any time. I want to thank everyone for joining us. As always, please stay safe and healthy, and let us know how we can support you. Have a great day.